Hello everyone, this is Team Lila, and we're going to be covering common surfaces as nerves. My team members are myself, Kyle, Shivani, Altaf, and Shanmuk. I will be going over bilinear surfaces and general cylinders. Shivani will cover ruled surfaces and symbolic operators. Altaf will cover surface revolution and in practice. And lastly, Shanmuk will cover non-uniform scaling surfaces and three-sided spherical surfaces. Moving on to the part one of the presentation. As an introduction, NURBS is a mathematical formulation that represents the geometry of curves and surfaces in 3D space. A NURBS curve generally consists of degree values, knots, and control points, which are also known as vertices. Increasing the degree of a NURBS curve increases the number of vertices. This allows for more flexibility, but also increases the complexity of the curve. On the figure below, there are two curves. The first one is of degree 3, and you can see that there are only 6 control points or vertices, whereas the figure underneath has a degree of 10, and there are 27 vertices. Having more vertices allows the curve to be manipulated without affecting other areas, depending on how many control points there are. Similarly, we have NURB curve. We also have NURB surfaces. NURB surfaces have the similar principles as NURB curves so that we can see similar results. But to define a NURB surface, it is a grid or mesh of control points in U and V directions. Increasing the degree of a NURB surface in the U or V direction increases the number of control points that it has, adding more flexibility, but also increases complexity. On the figures below, you can see on the left side is a surface of degree 2. It has 9 vertices. Um, the picture also depicts the U and V directions. Or the figure on the right is of degree 6, and you can see that there are a lot more control points on the surface. This will allow you to manipulate the surface more freely with more flexibility to generate a surface that meets the needs of the requirements. Additionally, NURB surfaces have direction that can affect the outcome of the generated surface. There are terms such as isoperimetric curves, which indicate the U and V direction, edge curves that draw out the edges along the surface. Each control point on the surface can have weights that direct the surface towards a weighted control point, as I'll show below. Uh, but the first figure on the left depicts the edge and parametric curves that I mentioned earlier. The, the isoperimetric curve is the orangish lines that you see there, followed by the black lines around the edges of the surface. On the figure on the right, it is an example of a weighted curve or weighted control point. The control point that is circled has a higher weight than the surrounding control points. And as you can see, the isoperimetric curves are drawn to that particular control point. This will allow the surface to take on a different shape or form. Moving on to the NURB surface equation, NURB surface is shown below as a degree P in the direction U and a degree Q in the direction V. This is a bivariate vector valued piecewise rational function in the form of the equation below, where U and V are in the ranges of 0 and 1. Breaking down that equation, the Pij form the bidirectional control net where Wij are the weights and Nip, U, and NJQV are non-rational B-spline basis functions defined on the knot vectors U and V. The surface can be written as the equation below. Now on discussion of bilinear surfaces, this is the introduction. Bilinear surfaces are one of the common nerve surfaces and are considered one of the simplest curved surfaces. It is defined by 4 control points located on each corner of the surface. Its 4 boundary curves are straight lines. The coordinates of any point can be derived by linear interpolation, and the 4 points are denoted as P0, 1, 2, and 3. A surface is derived by interpolating the 4 points using linear equations and the parameters u and v using the equation shown below. And the figure also illustrates that formula as well. You have the 4 control points, and you have your u and v direction, and you're able to calculate any point on this surface with the PU equation. To extend on the surface equation, P1, 2, and 3 are 4 points in a 3-dimensional space. The NURBS representation of the surface is obtained by bilinear interpolation between line segments given by the equation below, with knot vectors u and v in the below ranges 0, 0, 1, 1. The bilinear surface equation represents linear interpolation between 2 boundary lines that are opposite in each of the 2 directions. With bilinear surfaces, there are 2 different types of surfaces that it can be exhibited. The first being a planar surface. This is when 4 points lie in a common plane. The surface is bounded to that plane and exhibits a flat planar surface that is shown below. As you can see, there are straight line boundaries on the plane pi. So the plane pi is this dotted line here. It's a flat plane, and all 4 of the control points lie within that plane. So this surface that's shown in the middle, this mesh, is a flat surface. Um, Also, there are non-planar surfaces. So this is when the 4 points do not lie in a common plane. The surface is bounded by non-parallel diagonals that are formed from the 4 points, allowing for non-flat, non-planar surfaces such as a hyperbolic paraboloid surface, as shown below. In the figure, you can see that there are non-planar straight lines, boundaries that are on different planes. The surface is bounded by the non-parallel diagonals, which form a cube. So as you can see, you have the dotted lines here that are forming a cube. This surface is bounded inside of this cube and form the surface. Moving on to saddle design. A saddle is pretty much a hyperbolic paraboloid. The names are interchangeable. You can see the name is coming from saddle due to its similar looks to a horse saddle. The figure on the right is a hyperbolic paraboloid that's taking on many different shapes. You can see as the shapes come together towards the middle, it does form the saddle. But if you rotate this image at any point, it should always show like a saddle-like figure. To to design a saddle, you can use a ruled surface approach that's formed by movement of 2 parallel straight lines and the two lines must be collinear. So the four images below depict how this can be done. As you can see, you have a flat surface with two parallel lines that are collinear. There's a midpoint here, and you are, if you rotate the straight lines on both ends on opposite sides, so one going down, the other one going up, it will form a saddle. And to illustrate this, the image is rotated slightly so that you can see the curvature. And lastly, it is rotated further, and you actually get that saddle design that was shown on the previous slide. Next topic to discuss is general cylinders as a sweep. A general cylinder as a sweep is a pth degree nerve curve on the knot vector u with weights wi. The representation of a general cylinder is obtained by sweeping cu along a distance along w. Sweeping direction is denoted by parameter v, where v is between 1 or 0 and 1. There are two conditions that must be satisfied. For a fixed u-bar, a straight line segment from cu to cu plus dw. For fixed v, the translational invariance property is satisfied with the equation below. The desired representation is shown as the equation below, where u and v is within the ranges 0, 0, 1, 1, and the u naught vector is of cu. And the figure that just appeared is an example of a general cylinder as a sweep. On the far left, you can see cu is here with this cylinder. That's a closed cylinder. This is the V iso curve that goes along this way. And if you sweep this cylinder along direction W, it will form the cylinder, which was this right here is W, and this is the end point of this particular cylinder, and you can see the equation for this is Cu plus dW. There are other ways to generate a cylinder. You can use a profile curve. With sweeping surfaces, a tube does not have to be linear like a cylinder or circular like a torus. A circle can be used as a profile curve. So the circle is the shape of it, and another curve as a trajectory curve. So this nerve's curve here will serve as a trajectory that this circle will follow. The example below shows a circle as a profile curve with NURBS degree 3 and as the trajectory curve. So as you can see here on the next image, the circle follows the trajectory of the NURBS curve. And the last picture is just a solid version of that cylinder. With general cylinders, there are closed cylinders, also known as a right cylinder. This is obtained by translating the nerve circle a distance along d, a vector normal to the plane of the circle. A cylinder is defined by the equation below. Next, there are open cylinders. These are cylinders with circular and conic cross-sections with a sweep angle that is not a full circle, so it's less than 360 degrees. And you can see a right cylinder here and an elliptic cylindrical patch here. I want to end this presentation with a demonstration with the open closed cylinder and sweeping with this link here. So I'll click on the link. So with this example, you can see that this is an open cylinder. You can change the cylinder height. that's the profile of it, and it goes in the up direction. There are different degrees that you can add to the curve to change the shape of it. So I'll just add an extra degree here and make a slight change there. And you can see that the figure has changed. So this is a open cylinder. We also have the closed cylinder as well. And that concludes my portion of the presentation.
Hello, good evening. So I'll be talking about rule surfaces now. Basically, a rule surface is obtained by moving a line through a space. It can also be formed when two curves or two lines are joined through the line segments according to some corresponding points. So if you observe the figure on the left, B of u represents one curve and C of u represents another curve. And when this both curves are joined through line segments, the final output figure that is obtained is the rule surface. So these are the line segments that are used for joining both the curves. And the rule surface obtained by joining two curves or two lines A of u and B of u can be represented mathematically as x of u comma v equal to 1 minus v A of u plus u B of u. This equation can be rewritten in the below way. So this is some basic info about rule surfaces. In the following slides, we'll be learning more about the formation of rule surfaces and the terminologies included in them. So, coming to the terminology of the rule surfaces, as we have discussed earlier, if we sweep one curve along another curve, then a rule surface can be generated. And here, if you see in the figure that is on the right, a straight line is swept along circle. So here, straight line represents one curve and circle represents another curve. And after sweeping straight line along the circle, the rule surface that is obtained can be is represented in the figure B. So the line that we are sweeping, the straight line that we are sweeping is the generating curve, and the figure that is constant and along which the other curve is swept is called the directed curve. And see, if you while you're sweeping the straight line along the directing curve, there are some straight line markings. So these markings are called rulings of the generating curve. So this is all about ruled surfaces. And rail curve. So rail curve is nothing but the generating curve that is swept along. And this curve, the curve which is swept to create this curve is the curve that is swept to create a ruled surface. So basically, the nature of the ruled surface depends on the shape of the rule rail curve as well as the directing curve. And moreover, these curves can be any curves in the space. And what is ruling? So, ruling is the process of connecting the points on generating curve to the points on the directed curve. So, this points of connecting the directing curve to the generating curve, like if you see, there will be a directing curve and generating curve everywhere. So, this process of connecting directed points on directed curve to the generated curve is called ruling. And this process of connecting the points is important for the formation of rule surfaces. And ruling can be used to create surfaces with different characteristics. And coming to control points and nodes are used in computer aided design to define the shape of a surface generated by ruling. And these points control the shape of the ruled surface. So basically, control points are the points that are used to define the change in the shape of the curve. So if you see this figure located in the right, PO, P1, P2, P3 represents different control points because here, if you see here, the shape of the curve is changing a little and it's changing here again and it's changing here. So points at which the shape of the curve is slightly changing, that is, it is becoming slightly curved, is called the control points, whereas the knots represent the start and end section of the curve. So basically, they are the points along the direction curve showing separation between two segments of the curve. And so this is basically one curve and this is the other curve. So here, red dot represents the knot point. And the interesting thing about control points and knots is that by adjusting the points of the control positions of the control points and knots, the shape of the rule surface can be modified. For suppose if you uh, update the position of control point to somewhere here, then the curve will be this, the rule surface will be this way. So we can make many changes to the rule surface with the control points and knots. And coming to the formation of rule surface, if you assume two knob curves C1 of u and C2 of u, represented in this figure, uh, a rule surface can be obtained by interpolation between C1 of u and C2 of u. So we require this interpolation between points of equal parameter value, and the ruled surface obtained by connecting the points on C1 curve C1 of u and curve C2 of u can be represented as this equation, in the form of this equation. So the desired surface form is S of u comma v is equal to summation of I equal to O to n, summation of j equal to O to 1 r I p j1 u of v p I j. So here, and these V, N, U, P, W, I, J, P, I, J, they must all be determined for the formation of the rule surface. This basically represents knot vectors, the control points, uh, maybe the distance between them. So we do have an algorithm for the formation of rule surfaces as well. So this is the detailed view of the formation of rule surfaces using the algorithm. The first thing that you have to ensure is that both the curves are defined on the same parameter range u01 equal to u02, um1 of 1 equal to um2 of 2. That means the knot points on the curve, on the first curve, should be equal to the second curve. Uh, and if they are not, if they are equal, then the p is set to p1. If they are not equal, then the p is set to the larger of pi. So the control points are set to the larger value of pi, and we raise the degree of the lower degree curve to p. And uh, if the knot vectors are not identical, we'll merge them to the knot vector u. So basically, we'll be doing the union or the maximum multiplicity of both the curves, which is carried over to u. Like, if you consider an example of u1 equal to 0012244 and u2 equal to 0012344, so the final u, the control points, can be represented as the union of both the vectors of curve 1 and curve 2. And this knot refinement is important for both the curves, and this step yields the final values of all the terms that are required for the formation of rule surface. And here is an example. So this is input degree 2 curve and this is input degree 3 curve. So to form a rule surface between both the curves, we have to do the degree elevation first. Degree elevation means if you have a if you have an equal degree curve, that's okay. But if you have a low degree curve and high degree curve, we raise the degree of the low degree curve to the higher one. So that is what we do in the degree elevation. And we form the final knot vector u by the union of both the curve knot vectors. And after this merging has happened, a ruled surface can be obtained. So this is basically the control net of the ruled surface, and this is a ruled surface formed by sweeping 2-degree curve through the 3-degree curve. And talking about some examples of ruled surface, here is a right circular cone. Here we have a circle and a straight line. So if we sweep a straight line across the circular curve through the space, then right circular cone rule surface can be obtained. So here straight line represents the generating curve and the circular curve represents the directing curve. So here all this series of straight lines are called rulings, and they all are converging at a point apex to form the circular base. Another example of conide of rule surface is conide. So conide is similar to cone, but uh, the ruling is done in the non-coplanar way. So here the directing curve will be the non-planar, non-cylindrical, and non-conical curve. Maybe like a twisted helix or a warped curve. And all rulings intersect at a fixed line, that is the axis. And these rulings are parallel to a plane, and the twisted shape that resembles a cone but with a more complex and irregular shape is the conide. So here the generating curve is straight line again. And these are some real world examples of ruled surfaces. The cooling tower, this basically represents a conide, and the roof of a railway station. So here you can see some control points and knots. If you change the position of control point over here to a different point, the shape of the ruled surface can be different. So this is how we control ruled surfaces using control points and knots. And these are some more examples of ruled surfaces. So the first figure, helicoid. In helicoid, the generating curve is the straight line and the directing curve is the helix. So a straight line is swept across helix to form a helicoid. And same with hyperboloid. For hyperboloid, straight line is swept across hyperbola in the space. So the series of straight line rulings forms a hyperboloid shape. And for paraboloid, the generating curve will be parabola and the directing curve will be straight line. And these are some more examples of rule surfaces. Here is a degree 3 rule surface. Here is a degree 4 rule surface. So degree 3 rule surface is planar, whereas degree 4 rule surface is not planar. It's non-planar. And coming to rule surfaces, we have symbolic operators. So one of the most frequently used surface construction operators is the rule surface operator. And if we have two curves, C1 and C2, and we want to form a surface between both of them, then this surface mathematically can be represented as S of u comma v equal to 1 minus u curve 1 and plus u curve 2 c of v2. So we have seen this equation earlier too, and this surface is constructed in a homogeneous space if the curves are rational, but the surface we may get have continuous isoparametric curves even if the real curves are continuous in Euclidean space. Like if we use if we perform ruled surface construction via symbolic operators, even in continuous isoparametric curves, we get the rail curves continuous in Euclidean space. So basically, this is the formation of ruled surface in homogeneous space. If we sweep curve C1 of u along curve C2 of u, but with symbolic operators, the final figure obtained will be in this format. Like it won't be non-continuous as in this way, it will be continuous just like this. If we form the construction of rule surfaces, we are symbolic operators. So if you perform the same construction in the Euclidean space, we get the result shown in figure C. So, and this figure obtained can be mathematically represented as S of u comma v equal to 1 minus u n1 of u by d1 of u plus n2 u n2 of v by d2 of v.
Hey guys, this is Alta from Team Layla. Today I'm going to tell you about surface of revolution. A surface of revolution is a three-dimensional surface generated by revolving a two-dimensional curve, which is also known as a generator, around a fixed axis in space. The resulting surface takes on a symmetrical rotational shape, with the axis of revolution being its axis of symmetry. So, for example, if I take a straight line segment and rotate it around one of its endpoints, I can generate a cone. So as you see here, this is a straight line segment at an angle. If I generate it around about this point and this axis, you'll generate a cone like this. Similarly, if I take a circular arc and rotate it around its center point, I generate a sphere or a portion of the sphere depending on the angle of rotation. So here you can see it, a circular arc which is rotated around this axis of revolution. So to show this, I would like to take you to a website which shows how this is actually taking place. So let us see how this cone is formed with this line at this angle. So here we can see this is the axis of revolution and cone is being generated. I can just increase the speed so it goes faster. Yes. So here we can see how the cone is beautifully generated. Similarly, we can see a cylinder. Cylinder is a same, it's a straight line which is revolved around the axis of revolution, which is perpendicular to the base. And finally, I'll show the sphere, which is a circular arc rotated around an axis. Here you can see all the three shapes being generated using the surface of revolution concept. So moving on to the next slide, I'm going to talk about the properties of surface of revolution. First, the symmetry. Surfaces of revolution are symmetric with respect to the axis of revolution. This means that if you rotate the surface by any angle around the axis of revolution, it will look the same. Second, they have constant curvature. Surfaces of revolution have constant curvature along meridians, that is, curves that run from pole to pole along the surface. This makes them useful in studying the geometry of curved surfaces. Third, the area calculation. The area of a surface of revolution can be calculated using integration. Specifically, the area can be found by integrating the length of generator curve multiplied by distance it speed out during rotation around the axis of revolution. Fourth is the volume calculation. The volume of a surface of revolution can be calculated using integration. The volume can be found by integrating the cross-sectional area of the surface, that is the area of a slice perpendicular to the axis of revolution over the height of the surface. There are some important and properties of surface of revolution. Now let's see some terms that are associated with this surface of revolution. So a surface of revolution is generated by revolving a given curve about an axis. So the given curve is called the profile curve, while the axis is the axis of revolution. One more important point here is the axis of revolution, while you design curves. Using this concept, the axis of revolution must be the z-axis in order to create a surface of revolution under the curved system. So designing a surface of revolution under the curved system has some limitations that we must follow. Firstly, the axis of revolution must be the z-axis. Second, the profile curve must be in the xz plane. However, only the xy plane is displayed and when the curved system is brought up. To solve this issue, one can create a profile curve on the xy plane and rotate the curve 90 degrees away from the scene. Next, here I'm going to show you the construction of surface of revolution. So on the right you can see the figure and for a fix u dash s u dash comma v is the curve cv rotated some angle about the z-axis. For fix b dash s u comma v dash is a full circle which lies in a plane perpendicular to the z-axis with its center on the z-axis. Let us use the 9-point circle presentation with u is equal to 1 by 4 1 by 4 1 by 2 1 by 2 3 by 4 3 by 4 1 1 1 and weights wi is equal to 1 root 2 upon 2 1 root 2 upon 2 1 root 2 upon 2 and 1. Then the required surface has the form s of u comma v is equal to summation of I is 0 to 8 summation of j is equal to 0 to m r I2 jq uv pij. So the control points are determined as follows. For I is equal to O, Pij is equal to P0, J is equal to Pj. As the SU, V dash is of circular nature, Pij, J is fixed, where I lies between 0 and 8, both inclusive. All lie in the plane Z is equal to ZGJ. The weights are defined by taking the products of Wj and Wi. For fixed J, Wo, J is equal to Wj, Wi, J is equal to root 2 upon 2 into Wj, W2, J is equal to Wj and so on. Fixing U is equal to U dash and using projected form we get the below shown formula. And now when I use the generatrix and rotate it with at 360 degrees, I get this shape, which is probably a vase. So now I'm going to show some popular examples of surface of revolution. So a sphere is obtained by revolving a semicircle about the axis of revolution. In the curved system, this semicircle must be in the xz plane and the axis of revolution must be the z-axis. The following semicircle is a NURBS curve of degree 2. It has already been placed on the xz plane so that its two endpoints are in the z-axis. As you can see, the figure on the right shows the generated sphere showed in render patch and wireframe. The top center and the bottom center control points correspond to the two endpoints of the semicircle. Note also the circular wireframe lines, which are the loci of points in the semicircle. I'm going to show you one more example, which is a popular one. The torus is also a well-known surface of revolution and is generated by revolving a circle about an axis. This shows a circle in the xz plane which rotated around this axis. You will get the torus. The figure on the right shows the generated torus shown in render, patch and wireframe. The input circle does not intersect the axis of revolution. If you move the circle so that it is tangent or intersect the axis of revolution, generated torus will not look like donuts. For the tangent case, the generated torus is referred to as a spindle torus with one singularity. This is what we use while playing, that is the chessman. This is generated like this. This is a good example how the surface of revolution is put into practice. Moving on, I'm going to talk about the surface of revolution in practice. The shapes generated by surface of revolution are commonly encountered in engineering and manufacturing, as they are used to design a product and produce a wide range of objects and structures. So we can basically see this objects that are created using surface of revolution almost everywhere. The decorative items that we put in our living rooms, etc., all basically have a good symmetry. Those all are products of surface of revolution. One practical example is in the design of objects with rotational symmetry, such as pipes, cylinders, cones, and spheres. These shapes can be easily created by rotating a two-dimensional curve around a central axis, and they are commonly used in a wide range of products, from plumbing and HVAC systems to automotive and aerospace components. So they are pretty much everywhere, wherever uh, we need objects with rotational symmetry. Another practical example application of surface of revolution is in the field of optics. There's the lenses and mirrors, which are essential components of many optical systems, are often designed as surface of revolution to achieve specific properties such as focusing or reflecting light. By rotating a two-dimensional curve around an axis, it is possible to create a surface that can be shaped to manipulate the behavior of light in a variety of ways. So this is a pretty important application of this surface of revolution, which are used in optics. The surface of revolution can be also used in design of sculptures and decorative objects. So this the most things we see that are have rotational symmetry, all the decorative items, the sculptures, everything are examples of surface of revolution. Artists and designers can create a wide range of unique and interesting shapes by rotating the curves and exploring the different possibilities of surface of revolution. These shapes can be created using a variety of materials such as wood, metal, plastic, and they can be used to create beautiful and striking art pieces. So as you can see here, these all are some examples of surface of revolution, like the cylinder, the cone. Don't know what this is. This is a torus. This looks like a spear. These all, which have which are symmetrical about the axis they are generated, are examples of surface of revolution.
So, hi, this is Shanmukh Saithumala. Coming to the non-uniform scaling of surfaces. Non-uniform scaling resizes the selected object in a non-uniform manner. It allows us to choose the scaling for each axis, changing the x, y, and z axis values according to our design output. For example, at p of I, where I equal to 1, 2, 3, be a point in the three-dimensional space, and at f of I, where I equal to 1, 2, 3, be three real numbers, one for each coordinate. Scaling p about the origin by the factor f yields the point p equal to p of I, where p of I equal to f of I into p of I for I being 1, 2, and 3. If c equal to c of I is an arbitrary point, then p is scaled about c by the following equation, as shown below. The scaling is called uniform if three of I are equal, otherwise it is known as non-uniform scaling. Coming to the examples, there are several interesting surfaces that can be obtained by applying a non-uniform scaling to a surface of revolution. Here we can see an ellipsoid centered at the origin, which has an implicit equation of the form x squared by a squared plus y squared by b squared plus z squared by c squared equal to 1. Coming to the other example, uh, the three coordinate the three coordinates planes cut the surface into three ellipses. The ellipsoid is constructed by first producing the unit radius sphere centered at the origin as shown in the figure here. And then we do it by scaling it about the origin with the factors f equal to ABC. The xz and yz planes cut the surface in parabolas, whereas the xy plane cuts it in an ellipse. The figure below shows an elliptical paraboloid with the implicit equation as shown below. Coming to the elliptical paraboloid, it's obtained from the paraboloid revolution as shown in the figure by scaling about the origin with factors f equal to a comma b comma 1. And if the control points are stored in three-dimensional unweighted form, then the points would be p of omega equal to p1 of omega, p2 of omega, p3 of omega, and omega itself, which is equal to p of I of omega comma omega, where I equal to 1 comma 2 comma 3. And if the control points are stored in four-dimensional form, then only the first three coordinates change and the equation becomes the following as shown. Moving to the next topic, it's the three-sided spherical surfaces. Now let's see a corner surface problem where three-sided patch occur as patch as NURB surface. When three surfaces intersect as shown in the figure, it will result in a sharp corner or an edge, and those surfaces needed to be smoothened, and the smoothened surfaces are known as fillets. And rolling surface model would be the best for obtaining fillet surfaces. Here you can see the three surfaces are S1, S2, and S3 are following. Coming to the next figure, you see that the marble of radius r is rolled into the corner of the three surfaces, forming the new surfaces S4, S5, S6, and S7, where S7 is the corner fillet, a three-sided patch lying on the sphere of radius r. The arcs do not meet tangentially as they have a sweep angle of 180, and the corner fillet is represented as a 4 by 3 degree NURB surface. In addition to obtaining a corner fillet surface, we can even construct a tensor product patches on a quadric surfaces. A quadric surface is any surface having a second order implicit equation of the form as shown below. And a few examples of these surfaces would be spheres, ellipsoids, hyperboloids, circular cylinders, and cones, and etc. And all of these, whose generating curve is quadratic, are generated by two families of curves of maximum degree 2. And when you look at the sphere, the figure shows a stereographic projection to parameterize the sphere, mapping planar points onto the sphere. Let's construct a corner fillet. Let us consider a sphere whose radius r as shown in the figure, and the stereographic representation of the sphere would be as shown below. And the points UV points include the XYZ points, which is the intersection of the sphere and the line segment from u, v, 0 to 0, 0, 2 r as shown in the figure. Under this projection, we have the following correspondence, where a straight line passing the origin of the XY plane mapped with a longitude circle on the sphere, and all other circles on the sphere correspond to the circle in the XY plane. Now we denote the arcs of the fillet surface as C1 of t, C2 of s, and C3 of t, where 0 is less than or equal to s and t less than or equal to 1. Now, assuming the patch boundaries as oriented as C1 of t, C3 of t start at the origin, then we can observe that C1 of 0 equal to C2 of 0 equal to 0, 0, 0, and C1 of t lies in the xz plane, where C1 of 1 equal to C2 of 0 and C2 of 1 equal to C3 of 1. Now, creating circular boundaries for this three-sided patch, we convert them into the Bezier form. By using the following conditions, the fillet patch yields a flat surface, as shown below in the xy plane. S equal to 0 and S equal to 1 would be the boundaries of S2, S comma T, or the straight line. P equal to 0 is degenerate, and where T equal to 1 boundary is the circular arc. This is the relational Bezier representation of the fillet surface on the xy plane. Three-sided patch as a degenerate Bezier surface, the control points and knots. The general formula can be derived from computing the control points and weights of S comma T, and the computation is done in the 4 steps. Where first we obtain the Bezier representation of S2 S comma T, and then we convert it to the power basis form and substitute the power basis coefficients of S2 into S1 to obtain the power basis form of the fillet patch S of S comma T, and then we convert that point to the Bezier form. And the Bezier representation of S2 of S comma T requires 6 4-dimensional control points where P of I comma j omega, where 0 less than or equal to I less than or equal to 2 and j belongs to 0 and 1. We obtain the following: P 0 comma 0 of omega equal to P2 comma 1 of omega. That would be 0 comma 0 comma 0, where the weights are as shown below. And Pi comma 1 of omega for I belonging to 0 comma 2 are the control points on the arc C2 as shown in the figure. Now we project these 3 points, C2 of 0, C2 of 1 by 2, and C2 of 1, to the circular arc in the xy plane, and let x, y, z be the coordinates of these points, where the UV coordinates are constructed using the formula alpha equal to minus 2r by z minus 2r, y equal to alpha x, and v equal to alpha y. Now we compute the center O and the radius r, and then we compute p1, 1 omega, and later we do m equal to 1 by 2 into p0, 1 plus p2, 1, and we obtain p and p1, 1 equal to r into r, which is equal to 1 minus alpha of O plus alpha m, where alpha equal to r square by om square. And we do here a matrix multiplication, ai comma z omega equal to m2 into pi comma z omega into m1 of t, where m1 and m2 are the first and second order Bezier matrices. Applying the matrix multiplication, we get the following values as shown. From the above equation, S, the power basis form, is represented as shown. And from the above equation, we obtain the final equation S2 of S comma T equal to U of S comma T comma V of S comma T. And the Bezier representation can be written as S of S comma T equal to X of S comma T, Y of S comma T, and Z of S comma T, where the values of X, Y, Z are as shown. And by substituting the above values in the S of S comma T, we will get the power basis of the fillet surface. And the final Bezier representation is obtained as shown in the figure. Coming to the design examples, we here see 2 design examples. First one is the tire model, which is implemented using the mesh-based methods, and the next one is a coffee mug model, as shown in the figure. From now, next, Kyle shall continue explaining the GM lab. Thank you.
Hello everyone. For the GM lab today, I'm going to be modeling a wine bottle. To do that, I'm going to be using a common surface, which is a cylinder. So let me go ahead and start. To begin, I'm going to create a reference image. I'm going to use the image editor, and I already downloaded a reference image that I wanted to model. I'm going to select it, zoom out, and so this image here on the right, you can see it's got curves, it's got a flat bottom, opening on the top. It's an empty wine bottle. So to begin modeling this, I'm going to start by removing this default cube, and I'm going to add in a cylinder instead. The cylinder currently has 32 vertices. I want to lower it to 8 vertices, and you can see that the object has changed. I'm going to go ahead and switch over to the y-axis view so I can get a better view of the model that I want to generate. And while I have this selected, I'm going to add a modifier to this cylinder. So this modifier is the subdivision surface. And when I selected it, you can see that the model changed. It's became smooth. Using subdivisions, using the Catmull-Clark scheme, I'm going to upgrade the subdivision level to 2, and you can see that it has changed even further. Zooming in a little bit, I'm going to now switch into edit mode and start modifying this surface into this model here. So I'll begin by switching to X-ray mode. So doing so, whenever I select along this axis, it will select all of the vertices, even that are ones on the other end. I will scale this bottom piece out, and selecting the top, I'm going to move that down the Z-axis. So, and I still have the top selected, so now what I can do is I'm going to extrude upward. So, and then I can scale inwards, and then I want to extrude some more upwards, and scale inward again. And I'm going to do one last extrude up here, and scale it inwards. I'm going to switch back to the object mode just to see how things are looking. And it's not quite there. A few things can be done to get the shape that we need. So let me start by changing some of this up. Switch back to edit mode. So the bottom is kind of wide, so we need to narrow that down. I'm going to scale it inwards. And then to make the flat bottom, I'm going to scale this vertices downwards. And it gives us a nice flat bottom. I'll switch real quick so you can see. Okay, so let's see what we have next. So this bottle kind of straight here, and then it curves. So let me add a cut to this model. I'm going to do Control R, and I'm going to go along this axis, and I think I should probably do it like right around here. And I'm going to scale this out so that we can make that surface more flatter. Scale out. And I think I should scale this in a little bit. There we go. Switch back to object mode, and it's starting to get there. We got the flat bottom, we got the curving here. We just need to work on the neck now. So let's see, what we can do here is add some more cuts. I would add along this axis. And looks like a good spot here to start the neck. And we'll fan that inwards. Get this vertices here. Fan that inwards. And let's see how we're doing. I think it matches up pretty good. So I'm going to move on to the top view. So I'm going to switch over to the Z-axis. And since this is a bottle, we want to open up this top. So let's go ahead and select those vertices. Actually, let's go back to this and switch into edit mode. There we go. So I'm going to select these vertices. That's not quite what I want. Let me turn off X-ray. There we go. So this whole face is selected. I'm going to delete it. Delete just the face. And you can see that now the top is open. Next, while I have this view, I'm going to add another modifier. So this modifier is going to be the solidify model or modifier. This will allow me to add some thickness to the model. So you can't really see it too well. Let me see if there's a different, here we go. So you can see the thickness has been added. I'm going to increase it just a little bit. So there goes the thickness of the cylinder. Okay, switching back into the y-axis view. And let's go into object mode and switch the lighting on this. So now this model closely matches what we have as a reference. I think we can now start to smooth out this model. So I'm going to just select it and then shade smooth. Next up is to add some texturing to this model. Since it is a bottle, I wanted to have a glass texture. To do that, I'm going to add a material property. So go to material properties, add new, and instead of principled, I'm going to use glass. I'm going to lower the roughness. And now I'm going to switch over to a different shading view. So here goes the texturing. Blender does have some default scene that it uses. I'm not sure how to remove it, but that's what you're seeing here. There's like a forest kind of scene. I can change some of the scenes. I think it's on this one. I think this one looks a little bit better for the glass. I'll switch to that. And just looking at the bottle, flat, glass, it has an opening. And that concludes this demo. Thank you.